Hey everyone, welcome back. So far we covered all the major STL containers: vector, DQ, queue, stack, priority queue and map. Now it's time to understand something even more important. Today's video is about time and space complexity and why big O notation is very important. In competitive programming and interviews, nobody just wants correct code, they want efficient code. Solution 1 and solution might give same answers, but one is running for a 1 millisecond and the another one is running for a 1 second. Complexity help us measure and compare efficiency, okay, because both solutions are correct, but we want a efficient code. So through the complexity we can find our efficient code. Time complexity tells us how the running time changes as input size increases. We do not measure time in seconds, we measure growth rate. Here you can see in the graph, as our input size increases, the at which rate our time complexity increases, right? For this big O1, our time complexity is constant because our input size increasing and the time complexity is moving along the input sizes. For this case, you can say as our input size increasing as well as our number of operations are also increasing, so that time complexity also increasing and the efficiency of our code is reducing. In this case, we can say big O1 is the desirable time complexity and the n factorial is not a desirable time complexity. Let's look exactly how we are going to analyze time complexity for a program, because so if you have a PC, one is old and one is new, right? One is running i3 and one is running i9. If you try to run your code in both of the PCs, what you think, which PC will execute the program faster? You can say new one has a efficient processor, so it can make your code faster, and i3 is old processor, so it will run your program slower. But in the case of time complexity, it does not depend on the system itself, because we cannot or won't be able to analyze the how efficient our program is. So the time complexity term came into the picture, which solves the issue of how efficient our programs across all the systems. So it does not measure time in seconds but measure growth rate. As our input size increases, the at which our rate of time complexity increasing. So now let's see how we are going to analyze the time complexity. Let's say if you have a program and you are printing hello. For printing this hello, how many times our code executed? Only once, right? To print this hello, we need to run our code only once. So can we say our time complexity is WIG-O1? Okay, one more thing. The WIG-O1 is a representation of time complexity, similar to the function we write in a mathematics, right? It is also a function for representing the time complexity. So whenever you are going to measure time complexity, we are going to use WIG-O and the time complexity itself. So for printing a hello, our program only executed once, so we can say our time complexity is 1. Let's take another example. Let's take a loop for int I equals to 0, I less than n, I plus plus, and we are printing hello again. Now let's say value of n is 5. Now how many times this program will or this loop will run? For I equals to 0, it will print hello. For I equals to 1, it will print hello. For I equals to 2, it will print hello. For I equals to 3, it will print hello. I equals to 4, it will print hello. For I equals to 5, the loop will stop, right? So here you can count how many times our code is executed. 1, 2, 3, 4, 5, 6. So our code runs 6 times and the code stopped here. So we can write our time complexity big of 6, but the 6 is a constant and we are depending on n. So in this case we have taken n as a 5, but let's say if we declared n here and we are taking input from the user, at that time we cannot say our time complexity going to be 6 or going to be 10 or going to be 5, anything, right? It depends on the input itself. So in this case we will say our time complexity is big of n, because n can be anything. So we can say our code is running for a n times. Now you are thinking, we took n equals to 5 here, right? And the code is running for the 6 times. So it should be big O n plus 1. So whenever we are analyzing the time complexity, there is some rules we have to follow, like avoid constant. Whenever there is a constant in time complexity, we can remove them easily, because compared to our growth rate, the constant term is insignificant. Okay, this is one of the rules. There is others, we will look into them. Now let's look at another example. Now we look for a single statement, so its time complexity is big of 1, right? Because it executed once, this loop executed until I less than n, right? So we can say it ran for a n times, so we can say our time complexity is big of n. Now there is some common time complexities you are going to see when you are going to analyze a program. These are most common time complexities which you will be going to see when you are going to solve the program. There is other, will depend on the program itself. First one is big of 1, which is constant time. So this time complexity, we can say it is a constant time complexity. Then we have a big of log n, which is logarithmic. Then we have a big of n, which is linear. Then we have n log n, which is linearithmic. Then we have big of n square, which is quadratic. Then we have a big of 2n, which is exponential. Then we have a n factorial, which is factorial. So these are the most common time complexities. Now let's talk about the space complexities, because here you can see in our title there is time and space, right? So let's talk about the space complexities. With the term space, you can understand that it might be using spaces to store data, right? So let's say you declared a variable x which will be going to store data, right? So can we say it is a constant, because it is storing only one data at a time. If we talk about array, can we say its space complexity will be n, because the array size is n, so it can store data up to n size, so our space complexity will be n. There is another term for space complexity, it is memory space. Now there is two types of space complexities. One is auxiliary, another is input space. Auxiliary space is the space that you take to solve the problem, and the input space that you take to store the data. So the int x is a input space, right? Because we are declaring x to store our input. Similarly, array of n is also a input space, because array also storing a data. So we can say both of them are input space complexity. Let's say we have a program int x equals to 5, int y equals to 10, and we are multiplying them up. Or let's declare another variable z which is storing, and here we are printing. Okay, so let's analyze the time and space complexity for this code. So the time complexity for this statement will be 1, right? For this also 1, for this it is also 1, and for printing it is also 1, right? So overall we can say if we sum them up, 1 plus 1 plus 1, it is 4, right? But it is a constant, so we can take it as a 1. So this is our overall time complexity. Now let's analyze the space complexity. Here x equals to 5, so we can say it is a 1, and it is an input. Here also y equals to 10, taking 1, it is also a input. Here z also a 1, but it is not a input, because it is not using the input, but it is solving the problem which on the input we have given. So we can say it is auxiliary, right? So our overall space complexity will also be big of 1, right? But x and y are our input space complexity, and the z is our auxiliary space complexity, because we are using it for solving the problem. Now we have seen what is time complexity, what is space complexity. Okay, now there is three type of cases while analyzing the time complexity, which is best case, then average case, and then worst case. Whenever we are analyzing time complexity and space complexity, we always consider worst case. In best case, our code runs minimum number of test cases. Let's say we have 1000 test cases, maybe it will run only around 100, and it is still able to solve our problem. For average case, let's say it will run average number of test cases across all the inputs. For the worst case, it runs all the test cases. We have 1000, best case can run around 100 or maybe 200. Average can be in between of the worst case and the best case. For the worst case, it will always run all the test cases. So whenever we are analyzing time complexity and space complexity, we consider worst case. For this loop, we were also considering a worst case. That's why we are taking a n. Now let's talk about all the rules. So first is time complexity should always be considered in worst case. So whenever you are analyzing, always consider worst case. Avoid constant, right? Because we are talking about here growth rate, so constant become insignificant. And there is another, exclude lower values or lower time complexities. Means if you have a time complexity like big of n square plus log n plus 1 plus n. Okay, so the n square is our worst time complexity in this time complexity. So this lower value will be excluded and our time complexity will become n square, right? Let's say if you had a n value of 1000, so 1000 square then log 1000 or 1 or 1000. Compared to these number are really small, and even we add this number to this number, it won't make a difference, right? So that's why we avoid a lower time complexities. Now let's analyze time complexities for other problem also. Let's take an example. Int I equals to 0, I less than n, I plus plus. Then we have another loop which also running for n, and there is some statement. Okay, so for this case, what will be the time complexity? Let's analyze first our outer loop. Here you can see it will run for a n, right? So we have I, we have j. For I equals to 0, j will run for n times, right? For I equals to 1, j will run again n times or n minus times, because we are using less than. And for I equals to 2, j will again run for a n minus time. So I will also run for n minus time, and this will keep running. Can take time complexity n into n, so this also running n. So overall time complexity will be our n square, right? Because for every I, this is always running for n minus time, and this is also running for n minus time. So we can take n square time complexity. There may be some constant which already removed. Now let's take another example. Now I'm going to write in a sort. So our for loop, which is I, will be running from 0 to n. Similarly, we have another loop j, which is running till I itself. Okay, so let's analyze it. For I and j, for I 0, j is running 0, right? Because we are taking here I. For I equals to 1, j is running 0 1. For I 2, it is running 0 1 2. For I 3, it is running 0 1 2 3, and just till n minus 1. Similarly here n minus 1, right? So here we can say 1 time, 2 time, 3 time, 4 time. So 1 plus 2 plus 3 plus 4 plus n times. So sum of n numbers can be written as n square plus n by. Now we can remove the lower value, and we can also remove our constant. So our time complexity will be n square. Okay, for int I equals to 1 till I less than n, and this time we are updating I into 2. Okay, and we are printing something. Let's analyze it. When we have I equals to 1, okay, initially we have I equals to 1, then I less than n can be 1000, we don't know. Okay, then we are updating 1 into 2, so I become 1 into 2. Then in the next case, I become 1 into 2 into 2, right? Because at every iteration we are multiplying 2 into the I. So in the next iteration it become, right, initially it has 1, then it multiply 1 2 with the another 2, then the whole 1 2 to come here and multiply another 2. So it will keep going till somewhere n, and we can write 1, then we can write 2 k power 1, right? Because 1 into 2, here you can write 2 k power 2 and 2 k power 3, till we don't know till which condition it will go, so we can take a k. So we can say this power of 2 will keep going till the k. Okay, and I will stop at the end. So now here you can see our loop will keep running till I less than n. As I become greater than equals to n, our loop will stop, right? That should be the condition to stop a loop, right? Because it is running until I less than n, and if I become greater than equals to n, the loop will stop. So we can say I equals to 2 की power k, because it updated the value till the 2 की power k as the I was keep running, right? These are our I itself, so we assumed k here, so I equals to 2 की power k. So we can replace that I, so we can write 2 की power k is greater than, as 2 की power k greater than n, the loop will stop, right? So we can simplify it, and if we take a log, it will become base to n. So we can say our time complexity is log to n, because our loop is running for a k times, right? Because this 2 की power k is equivalent to I, and from the I we are deciding, so our I equals to 2 की power k, so means our loop is running for the 2 की power k. So from that expression and from the end condition, we deduce that our time complexity will be log base to n. Okay, let's look at another example for I. This time we are running from n and going till the 1, and also we are dividing the I by 2. So let's analyze it. We have I was initially n, then we divided n by 2, then it be divided again, then it become n by 2 into 2, then again n by 2 into 2 into 2, right? At every iterations is dividing the same n, so it will keep running till n by 2 की power k, right? Because we can write n here, n by 2 here, n by 2 की power 2 here, n by 2 की power 3 itself, then it will run till n by 2 की power k. So our stopping condition is I less than 1. Our loop is running for I greater than equals to 1. As long as our I becomes less than 1, our loop will stop. And what is the value of I? It is n by 2 की power k, right? It is going till the n by 2 की power k, so we can write n by 2 की power k less than 1, and we can simplify it and can write n equals to 2 की power k, and if we take a log, it will become k equals to. So in this case also our time complexity will become log base to n, right? The way of writing loop is different, but the number of operation is running is similar to this loop. In this case we are running 1 to n, and we are incrementing the value of I by multiplying it by 2. In this case we are running from n to 1, and we are dividing the value of I by 2. Okay, so the way of writing is different, but the number of operations both loop is performing is similar. Now let's take another example. Okay, we have x equals to 0, then we are running loop I 1 to n, and we incrementing x here. Okay, there is one more thing. We are updating I by multiplying 2. Then we have another loop. Let's take it as a j, going till j less than p. Okay, and we also updating j multiply by 2. Okay, so now what will be the time complexity in this case? Here you can see we are running from 1 and we are multiplying by 2, so we can take this time complexity itself. So we can say our this loop will produce log base 2 and time complexity. Now for this case, the j also iterating similar to this, but it is going till the p. Okay, we can take time complexity, we go log base 2 of p. Now this time complexity is for the, okay, it's p or x, it is x. Okay, so we are taking this time complexity till n. Also we are updating x till n itself, so here we can take log base 2 of x. So what is the time complexity of x we can take? It will be big of log 2 of n. So this will be our overall time complexity. Okay, because this loop's time complexity is depending on this x itself, and this x is producing the time complexity of big of log base to n. Now let's take another example. We have a 4 int I equals to 0, I less than n, I plus plus, and there is another loop j equals to 1, j less than n, and j equals to j into 2. This time it is really simple, right? This is running for n times, and this is also running for n, and we are updating j with the multiply of 2, so we can take a So overall time complexity will become big O of n log base to n. So our time complexity is n log n, right? Let's take another example for the cases of while loop. We have x equals to 1. We are applying a while and condition will be x less than y and x equals to x into 2. Okay, so we don't know what is y and x is running till the y, and also we are updating x by multiplying by 2. So let's analyze it. We have x, initially it was 1, then it become 1 into 2, right? We can write 2 to power 1. Then in the next iteration it is become like this, and we can write 2 to power 2. Then 1 into 2 into 2 into 2, and it become 2 to power 3. So we can say it is going till the 2 to power k. Now loop is running till x is less than y. If x becomes greater than equals to y, our loop will stop, right? So and our x is going till 2 to power k, so we can write 2 to power k greater than equals to y, and we can simplify it and we can write this. So now we can take a log, then it will become of y. So we can say our time complexity is big of log 2 of y, right? If we have taken y as a n, it will again become log n time complexities. Even we are using while loop or for loop, the time complexities will still depends on the number of iterations. Okay, let's take one more example. We have I equals to 1, k equals to 1. We are running a loop while and k going till n, and we are updating k equals to k plus I and I plus plus. Okay, so let's analyze it. We have I here and we have k here. For I1, k is 1 plus 1, right? Because k was also 1. Then for I equals to 2, k will become 2 plus 2, right? Because this will become 2, then 2 will come here. This will become 4. So for the next iteration, I equals to 3, it will become 4 plus 3. And for I equals to 4, it will become 7 plus 4, right? Because it will become 7, then 7 will come here. So that's how it is increasing. So we can approximately take k equals to m into m plus 1 by 2. Okay, let's change it a little bit. Let's take it as a 0, and let's take it here also a 0. So let's take it here also a 0. Then it will become 1 plus 2 plus, okay, let's remove it. Let's analyze it again. For 0 it will become 0 plus 1. For next case it will become 0 plus 1 plus 2, then 0 plus 1 plus 2 plus 3, then it will become 0 plus 1 plus 2 plus 3 plus 4. So we can write 1 plus 2 plus 3 dot 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 till the m. Okay, so we can write m into m plus 1 by 2, right? So our k is going till the m into m plus 1 by 2. So our condition is k less than n, loop will keep running. If k becomes greater than equals to n, the loop will stop, right? And the k value is m into m plus 1 by 2, and let's simplify it also. Then it will become n, then m square by 2 plus m by 2 equals to n, right? Now we can remove lower value, we can remove a constant, so it will become m square equals to n. So m equals to root n. So our time complexity is big of root n. Okay, that's it for the examples and also for the time complexities and space complexities. The time complexity, space complexity is really important topic for DSA. After every DSA problem, you have to analyze the time complexity and space complexity. So for now you might not be able to understand all of it, but maybe some part. Now whenever you are solving a problem, after solving a problem, make sure to analyze the time complexity and space complexity. As you keep doing it, it will become habit and you will be able to easily analyze the time and space complexity. Okay, thank you everyone, have a nice day.